PGY too.
HIV clinic all the time.
Besides Peter.
Yes. Remember that what you're going to learn from Tarek in these 4 sessions, you're going to use later in the year in the neurobiology seminar that you have with me. And remember too that I'll give the first seminar, but after that, you guys are going to do the presentations in that neurobiology seminar. There'll be 90-minute sessions, and each one of you will have 45 minutes to present a topic with a 4-page handout and take questions. So this is good practice for you. See how Tarek does it and to provide a basis.
So I'll just get started. So again, this is just really a framework. There's some factual information in here because I think that that's important, so that we can talk about things, but it's more about not memorizing, but more about doing the process. And we're going to do a lot of processing backwards and forwards on different levels of scale. That's the main idea here. So I'm recording it. I'm mainly recording it for my mom because she always asks me to record stuff. So you can wave to my mom. I'm going to give a couple
Best want to wave to mom? There you go.
comments up front. I've recently watched a lecture series by Robert Sapolsky, so I stole a couple of his jokes, so I got to give him credit for that. And I also will give credit for Dr. Hobbs. I don't know if I mentioned this to him, but I went to med school here, and his lectures were pretty much the only lectures I went to in med school, and they pushed me towards psychiatry. They were pretty good. So it was and Ben also, sort of story time. Peter probably
Oh yeah, definitely.
Same.
Yeah. Are you still doing it, Dr. Hobbs?
No, you're the last year.
Oh.
I was.
So again, I'm calling this, the metaphysics of psychiatry, because the idea is that it's really going to just be applying ideas about flippantly without really any, sometimes real understanding of what's going on. And, as a disclaimer, I'm not a biologist, I'm sort of a chemist, but not really. So a lot of these things I don't really have expertise in. I got most of my information from Wikipedia, but again, it's not about the details. It's really about just understanding how these things fit together, how DNA can influence proteins, how proteins can be the receptors that make proteins are enzymes that convert things into neurotransmitters. Neurons make up neural circuits, make up modules that affect our behavior that help us get through society and back and forth how these things do. So that's really the idea behind it. I want this to be sort of interactive, but at the same time I don't want to go on long sides because I've got a lot of stuff to get through. If you have a question that's sort of pertinent, definitely step in and ask it. If I'm lying, call me on it. So just to start off with, I'll just ask these questions. You can give a show of hands, a yes, no, not sort of reciprocate. But so who here believes in free will? Predestination? Good? God, evolution. Who thinks it's all explained by nature? Who thinks it's all explained by nurture? Who thinks that it's a wonderful, wonderful combination of interplay? All right, we're done. All right, so I'm going to go through a few different processes, and you can tell me whether they're a disease that, or just a process that lies in the mind, the brain, and the body. Schizophrenia? All right. Seizures. Heart attack. Pseudoseizures. Hip. Stop breathing. What about yawning? All right. So, what's Prozac and how does it work? Someone can jump out. I'll call somebody. SSRI. Okay. SSRI. How does it work? Or the selective. What's depression? Anyone want to take a stab at it? Okay. Not an easy question. What causes the question? are we rational?
You like to think we are, yeah.
So this is going to be the very last slide that I'm going to present on my last lecture, and I'm hoping that there will be some more discourse on these questions that you can hopefully go on for a long, long time to remember about them. But I already like the way that you all are thinking about them. It's pretty good. So let's begin again. For me to sort of, I guess, come up apart, but seriously, it's to give you all a framework to understand it. Because this stuff is very, very complicated. And psychiatry is sort of fun science. You know, it's not a hard science. Probably one of the softest of sciences. And you know, what you're being asked to do is to explain really, really, really complicated things. And you know, it's not just sort of behavior, it's behavior among humans, it's human behavior in a social context, and then it's pathological human behavior in a social context. And, you know, that's a pretty tall order for things to do. So the idea is not necessarily to get an answer to know exactly what happened, but to be able to have you sort of think about things and not just say, oh, serotonin, but sort of kind of understand like maybe where we're going and maybe how this stuff works. And so, you know, again, I don't think this stuff is magic. It's not just sort of things that are happening. I think that something is really going on. I don't sort of think you can explain it or understand it now, but I'm not sure if we will be able to understand it in the future. Steve, you want to tell me what magic is?
Now the particularly advanced and get to the releasing.
Right, so I think that our brain is pretty much there. It's pretty advanced. We're sort of, it would be sort of like we're asking a caveman to explain like thermodynamics. You know, he's going to see fire. Ooh, fire, hot fire, burn. That's sort of what we know in psychiatry. You know, depression is bad, serotonin. It's probably a lot more complicated than that when you actually get into what's going on. So the idea, again, is just to have a way to think about these things, a way to think about how are our interventions working, whether it be medicine, whether it be therapy. How come depression works the way that it does? How come depression does? How come depression is comorbid? Start to understand these interplays. And I'm not you, but I don't know the rest of the interns, so they come in and I'll say hi. But hi, welcome. And then again, it's to become more self-aware of what we're thinking. So when we're thinking, we have to say, I want to recognize that. When, you know, it can help us be aware of our thought process. So I wanted to take a quick minute to talk about learning, because, you know, this is a lecture, and I think that a lot of us, I have found that I got to be a lot better learning by sort of being an active learner, and probably the biggest thing is intention. You know, students, anybody who comes to anything, you can ask any high-level musician, actor, whatever. When you're practicing and you're learning something, do it with intention. Know what you're trying to get out of it, focus on things, and don't just sort of absent-minded review. Because, you know, like my roommate Casey will sit in front of the TV and have two books open, a video, and a movie, and a game. And it's like, he's just sort of, I think, calling the guilt of not doing something. But, you know, when you're doing something, do it with intention. And the next point is one of sort of integration, redundancy, and consolidation. And that's really what the point of this is to help us not see slices of things or tiny pictures, but be able to zoom out and see the bigger picture and to integrate things. And so an example of this is sort of like, you know, neglect, for example. Dr. Hoffman talks about this stuff. But when I want to think about neglect, I can sort of remember everything about neglect, or I can understand some concepts about the brain and have multi-level into it. So the more you can encode something in the brain, the more you remember. So, you know, where in the brain is neglect normally things? Like, I wouldn't really normally do that. There was a patient that I had that had neglect that I walked into the room on the left side and they didn't see it. Because now I know it's sort of a left side phenomenon. I know it's on the right side of the brain. You know, if I took any one of those facts, I could extrapolate the rest of the facts from a single point of information. And I think the more we can multiply encode information and sort of have it make sense together, you don't need to memorize everything. You can sort of understand concepts and then draw, you know, away from that. So, you know, I use another example as a map. You know, if you start here and you want to, you know, find how to get here, you can memorize the route here, And if you want to go here, you can memorize a whole new route, and you can know the map here, and then just learn how to get from here to here. And I think that's the more of this type of learning that I would encourage you to do, and that I have found has been what I take away. I don't know that you all remember about cramming, but when I crammed, that there's just shoved in information, and how much of that cramming is beyond me now. I don't know any of that stuff unless I really use it in consolidation. And then repetition, of course. Personalizing or emotionalizing, when I'm memorizing something like just root memorization, I will sometimes find an emotional component. So Dr. Dammer will say, what are the criteria for borderline? And I imagine in my head that he's hinting me on it to sort of, give me a motivation and a centralizing sort of.
I think you picture of it.
Yeah, perfect. And then the next one is drugs, and I don't know if I can officially sanction this, but there we go. I use caffeine as a learning tool because I got caffeine in a later lecture and what it does. You want to help me hand these out? You can take one at a time. Turn your head, Dr. Dammer. 5 hour energy. If anybody ends up psychotic on 5 of these, I didn't do it.
Yummy.
Liver rocket.
Do you want?
I've got this.
This is something that, I think we all get into trouble doing. Lots of black and white thinking. This is something that I'm going to discourage you from doing. And the idea is that, things generally have, we like to think in black and white, and we like to think in categories. And so, I'll tell you a quick story. It's not mine, but it involves one of sounds, and where we draw a line between different sounds and culture. So, in English, we have certain boundaries of sounds. In Vietnamese, they have very different boundaries. And that's why certain people can have a much harder time learning a second language after a certain time, because your sort of labeling of a sound is done pretty much, not completely, but after a certain age. And so a quick story is a guy wanted to take testicular biopsies from gorillas. So odd story, but here's just the story. And so he's at Stanford, it's Robert Sapolsky, and he's calling the attending of urology. And this is a Finnish guy, and he's asking the attending, what do I need to do to learn? And the attending's telling him all about these kits he needs to buy to take the biopsies, etc. And then at the end he says, I recommend that you practice on a bear. And this guy's thinking, what? What did he say? Oh yeah, we do it, all the residents do it, we have them practice on bears. I know it sounds crazy, but it's very much like the real thing. He's like, what? He's like, a bear, like an apple. And then he's like, oh, and so he realized that P and B, and similarly in Arabic, P and B share, we don't use the P sound in Arabic. So again, you can see how these categorical thinkings can lead you into trouble. I'm going to do a little bit of quick drawing on the board. And I'm going to ask you all to tell me what the next piece of information in this sequence is. All right, what's the next number in this sequence? What if I do this? If Roxanne was here, she'd probably know this. The next number is 42nd.
Oh.
And if I was giving the
Streets of New York.
in New York City, everyone would instantly have known that. So here's another one. If I say, oh, what am I doing here? What's the next pair? What if I was giving this to a group of, whatever, biologists? No idea. What if I, was in Israel and I thought it stood for the Territorial Defense Organization, and the Emergency Committee for Israel. Right, so our frameworks of thinking are very much pointing us in the direction of where we want to go. And I think that you can see how that's pretty easily applied to psychiatry if we put on our blinders and just sort of are looking for patterns that we're always taught sort of are going to go together. So I just encourage you to be critical about that. Here we have a pass-fail system. So what's the difference between the 69 and the 70? A degree, right? But really, truly, what's the difference between a person who's averages a 69 and a 70? Not a whole lot, right? So by creating this artificial boundary, we've inflated the difference between the two. And I think that, in DSM, you can see very much that. Colors, similarly. I can draw this on the board, but you can draw the Roy G. Biv, and we are making these very artificial lines. Nature does not know where a line exists between red and orange, or orange and yellow. And they do studies where if you take people in America and you sort of show them colors and have them recall them later, we can much better recall colors that we can label easily. Things that are on the border, we do not recall as easy. And if you go to a culture that draws their borders differently, our red might be hard for them to remember. So the other idea is one of analog versus digital, whether things are on spectrum or not. So what do you all think about psychosis? Can you have a little bit of psychosis? Yeah, what's psychosis?
Impaired reality testing.
Impaired reality. So something in reality you're misperceiving it. You are not taking in reality truthfully. Does anyone want to argue that you can't have any psychosis? Do you all think y'all are just a little bit psychotic right now? Yeah, okay. Well, this makes this less entertaining, possibly.
Cool. Yeah.
All right. I want you to take a look at this picture and focus on these three dots right here. Try not to blink. We're going to do this for about 30 seconds. So you can look at these pictures for about 30 seconds. Focusing on those dots. Focusing on the dots. Good. You can blink if you need to. Try not to. Good. 5, 4, 3, 2, 1. Blink, 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 blink. Blink, blink, blink. Okay. Now, sort of look away. What do we actually have here?
Nothing.
Nothing. What did we see? Was that in your head? Was that a thought in your head? Did it seem like a thought, or did it seem like something you saw?
Oh, I saw it.
Okay, you saw it, and it came in through your eyes. It came very much in through. That's called a negative after image.
Yeah.
So again, what about this idea of drug versus not a drug, right? I won't take any drugs. I'm not taking any of these drugs. What do you all think? What's a drug? I ask people this all the time. What's a drug? Right? I mean, what about oxygen? Okay. Oxygen. Your oxygen gets low, you act funny. Oxygen gets really low, you die. All right. What about food? Food that has preservatives in it. Like, talk about polypharmacy, right? You eat a hamburger, tons of stuff going on there. Your body knows no difference between these amino acids, vitamins, etc. The idea between natural or not natural, right? Prozac versus St. John's wort. Like, your body has no idea. Natural does not mean safe. Strychnine is natural, cocaine is natural, opium is natural. And the other question that I'd ask is, it doesn't even have to be a drug. It can be a behavior. Like, think about sex, right? When's the last time you had an orgasm from taking a Prozac? Right, so these things are very psychoactive. They very much change our mood. They change our biology. Natural. Who here does not have indoor plumbing? We draw these dichotomies. Our patients will draw the dichotomies. And I think it can be helpful to sort of have the conversation with them. You eat ice cream, it changes your mood. I think it's very natural to think in black and white. I think it's very much human. I think and again, it's just the idea between, you underestimate the importance of it. And by focusing on categories, you can lose the picture. So before you really try to do that, you got to memorize a little bit of this stuff. It's pretty basic. I'm going to keep it pretty basic, but without knowing a few facts, you can't sort of start integrating this stuff. And then we're going to integrate it. Then you'll be able to think about your patients this way. You'll start making predictions. about these things, and then you can get some understanding of that. And the other thing that sort of is interesting, I don't know if this, let me see this really quick. That's not coming out later. All right, so our first one. All right, you've got this chicken, all right? It's just hanging out, it's chilling, it's doing chicken stuff. On the other side of the street, there's a rooster. The rooster sees this chicken and it starts doing a rooster chicken dance. It's going nuts, it's doing all of its sexual prowess type stuff. The chicken sees the rooster doing the dance, it gets obviously excited in a chickeny way, and it goes over to meet the rooster. All right, so our first question is, why did the chicken cross the road? So it's sort of cheesy, right? But I think it sort of allows us to see how our framework is going to answer that question. Because, you know, how might, like, say, an evolutionary biologist answer that question? Something about passing on your DNA, right? The roosters who were successful at doing the dance, and the chickens, you know, were better at spreading their genome on, and the chickens were able to identify that, got to, you know, continue passing on their DNA. Or how might sort of a neurobiologist answer that? You see this rooster doing its dance, you release estrogen and testosterone, which gets into your, you know, pathways that, so the idea is that, you know, depending on your framework, you can come up with very different answers for a question. And the truth is that it's all of these things going on at the same time. And the idea is to be able to sort of flip between them and integrate these things to come up with some sort of sense of what we're doing in psych. And so these are the big categories that I'm going to go over. I doubt I'll get to all of them. But we'll get as far as we can, and I think it'll get the point across. So I'm going to make some analogies to cars as we go along. Some will be better than others. So the first one is, you know, that genetics to some extent are the blueprint of the car. But it's more really to it than that. It's sort of also you responding to it. So the genes are the way that your body in some way can respond through differential protein synthesis to different situations. And so, you know, I use some cheesy examples. I don't know if y'all looked at the handouts. Of, you know, you see the low gas light, and that's sort of the neurotransmitter signal to secrete the, you know, to make the proteins happen that make you pull over and get gas. So it sort of is a way of interacting with the environment through protein synthesis. And then sort of the neurons and neurotransmitters is the input, right? So when we push on the gas pedal, that's the signal that we're sending to the car to do something. The epigenetic changes is the augmentation of that. So, you know, if we push on the gas this much, you know, 5 years later if we push on the gas, it might have a linky throttle connection. And so you get a different response from the same input. And that's sort of how epigenetics is working. Endocrinology and physiology is sort of like the fluids, the engine temperature, those sorts of things. Maybe the temperature of the tires, that sort of thing. The circuits are going to be sort of how things communicate. So you push a turn signal, sends a signal to the computer, it sends a signal to the light. You turn the steering wheel, you know, it goes through your ball and pinion steering to your axle to change. So that's sort of understanding how one thing is connected to another. The behaviors, you know, what's the car doing? Is it driving fine? Is it handling well? Is it sliding? And then the environment, you know, what kind of road are you on? Is it wet out? Is it dark out? All of those things. And obviously all of those things matter, and all of those things are going to have an interplay on each other. And then sort of, you know, balance in time. What's happened to this car over time, and what's happened to the environment over time. You know, this environment has changed over time, and the car has changed over time. So that's just sort of a quickie of that. We get a picture, a video. Let's see.
He's only 1 point ahead Ted on the championship, and I think there's a bit of a personal battle, but what the picture is, full sideways action from Marco Martin, a bit hot on the entry.
So clearly a lot of things going on. I just really wanted to show that. But you know, a lot of things going on, a lot of things interacting. You know, he's got the input, the driver's input, the environment that's trained him, and all those sorts of things. So we can use phobia as our first example, and I'm not going to use a lot of hard science on this because we haven't really learned the science yet, but this is just a way of thinking of psychiatric illness. So the first thing that we're going to do is we're going to forget our DSM criteria, and we're just going to look at it. So what is phobia? You know, if you were a kid describing phobia, what would it look like, or what would it feel like?
Scary.
Scary. So that's the emotion. intense fear. So that's the emotional way of describing a behavior. What about the physiologic sort of feelings? Uncomfortable. But more sort of physiologic, more doctory. You're not too far from med school. Asking me to be a doctor is different.
Kind of tachycardia.
Increased heart rate, right? Your sympathetic responses, dilated pupils. So what would it look like behaviorally? What might happen in that context? You run away, okay. That's how we're going to think about things. What is the behavior? You know, phobia is easier than some things like depression, but you know, think about it on some way that way, because that's the functional stuff that's happening. When we're looking at these circuits, we're going to think function, because something happened to increase your heart rate. It's not magic. Something happened. It got into a system that did that. Something happened to trigger a fear response. You know, we're going to talk about the neurotransmitters that get released in what circuit, the learning that happened to cause that fear. So that's sort of the way that I want us to start thinking about these different phenomena. And then we're going to go to the second before, and that's sort of the neurology, neurobiology part of it, you know, the why. Why did this happen? So, you know, let's say you're afraid of dogs. You see a dog. Photons come into your eyes take it, it sends it to the system of your brain that starts labeling things. Is this a dog? Is this not? It gets its first pass assessment that's largely unconscious. What do I make of this situation, dangerous or not? That happens largely on an unconscious level. You know, it gets an emotional tone placed on it through the limbic system, through the amygdala. It then, you know, sends its signals off to the nervous system. Like, I don't know if you all have gotten a sort of, you've seen something and you've had your adrenaline hit. That happens way before you've processed the situation. And only after you've had that sort of immediate neurologic response that happens in milliseconds to a second are you then able to cognitively process the situation. This is a dog, I'm scared of dogs, run. But, you know, the question that I would ask is that, you know, are we afraid because do we run because we're afraid, or are we afraid because we run? And, you know, people have asked that question. It's actually not that silly of a question, because our behavior often happens before we're cognitively aware of it. And they've shown this time after time in an experiment, and it's sort of scary to think about that, like, what we're doing is actually happening before we're thinking about it. But they've shown that in a few different situations. So it's just something to think about. And then, you know, it's the environment. How come you got afraid? Well, there was a dog there. Or maybe there was a situation that reminded you of a dog. Or, you know, maybe, you know, you heard a song that you were listening to when your girlfriend broke up with you. And, you know, that triggered the thought of the girlfriend that sort of triggered the second before, which triggered the behavior. And then the more complicated part is the past. So how did our brains get to a point that it is this way? That this sort of input is going to run through this system to cause this behavior? And that's a very, very, very complicated question. You know, it involves all levels. It involves learning, so a cognitive aspect. It involves, you know, our underlying genes. It involves our, you know, stress system, how quickly it can trigger, how easily it will trigger. And a lot of that stuff is just this mixture of genes, nature, and nurture, and experiences and interpretations that change our brain and it changes our personalities. That's very tricky, and that's sort of what our field is, you know, looking at answering and at doing oftentimes. You know, when they ask us, you know, what caused this person's depression? Well, it's not that easy. It's actually pretty crazy. And so this next point is probably one of my biggest sort of so the more complex or nuanced or chaotic a phenomenon, the higher the probability for heterogeneity in etiology. And, you know, I could talk about this for an hour because I think it's one of the most important things in psychiatry, and I think it is the reason why we are sort of stuck in psychiatry. Depression is not one thing. Depression is many things, and you all are going to come up with 100 different things that depression could be. And we're going to do a lot of analogies between depression and pneumonia, and sort of seeing how symptoms do not necessarily dictate treatment. Etiology dictates treatment, and we are not at all in an etiological sort of phase in psychiatry, and until we can start thinking that way, thinking functionally, you know, all of our studies are very, very, very flawed, and I'm going to talk a little bit about that when Peter gives his evidence-based medicine lectures, sort of just pointing out the inherent flaws, and you know, we do the best that we can with what we have, but sort of understanding
not as simple as all depressions are depression. So what's the goal? We all think categorically. I absolutely, of course, think categorically. That's how we have to think. But do it in a good way. Understand how you're using these categories. Try and see the big picture of things. The next one is another big point, Mike. Try and think functional, not reductionistic, right? So what is depression? Depression is serotonin. No. Serotonin is absolutely, in some forms of depression, serotonin is a key player. But serotonin isn't anything. It looks like a simple little molecule. But it interacts in lots of different ways, with lots of different
pathways that therefore can allow it to have actions. Lots of things can make serotonin, lots of things can break serotonin down. Serotonin has to do a lot of things to be functional. These circuits have to be working in a certain way for it to be functional. So don't think of it as a disease of serotonin. It's a disease where serotonin is one part of it, right? A lot can make a car not drive. I can take out the engine, I can take out the transmission, I can, smash the steering wheel. The car's not going to drive. But if we want to be a car mechanic and fix that car, we've got to think a little bit better than car broken, So that's sort of the idea behind it. And if I had more time, I would talk about adenosine and what it might be doing. And I can also talk about some of that in the brief. All right, we're going to rush on to the next lecture.
What's new?
Oh, I didn't bring it. I had lost it. Andy was fortunate to bring that. It's a super potent pre-workout supplement, and it has a psychoneuro complex in it, which is pretty
Psychoneuro.
It's integrating the brain and the body. Does anybody know what Deus Ex Machina stands for?
God from the machine.
God from machine. Does anybody know what Veni Veni Locum Way stands for? Come on, do the locomotion.
So this is the picture that was in the
Handout. So I'm going to just try and explain it in the way that I think about it, and I think it might be helpful to understand. Yeah, sorry, I didn't send you all the handouts. There's handouts with each of these lectures. So again, what I want you to look at mainly is just what's happening. So these are just molecules, right? This is oxygen, this is carbon, right? This is a range. Pretty much, and this is what DNA looks like. So what I want you to do is take this T here, and superimpose it on, you can't really see them here, on this T here, but understand that these are all contiguous structures. There are no separations. We separate them in our brain, but when you see this DNA, it does not know this picture. It knows this, and if you zoom in further, this carbon knows protons, electrons, and neutrons, and you can keep zooming in. And that's sort of the level of understanding. If I want us to start connecting things and not looking at snapshots, but sort of seeing this integrated picture. And we're going to do some of this, and you're going to see how cool it sort of is when we're able to start putting these things together. So again, we're just looking at levels of organization, understanding that they all exist at the same time. So here's our nucleotide bases forming a double helix, which are then going inside of histones, which are super important. So histones are the first level of organization of DNA. So we're pretty much spools, giving out spools, just spooling up DNA, right? But for this stuff to get read, it physically has to get read. So if you had a spool of string, right? So the example is a mile of string in a marble. Right? If I have a mile of string in a marble, and I said, oh, here's this gene, let's make it. So you've got to have a way of exposing that. It's buried somewhere inside all this stuff. And so a lot of the stuff that we're going to be talking about is just very physical chemical interaction of exposing this stuff. You put a hydrophobic molecule next to something else, it's going to sort of push it away, and you're now creating a way. Again, it's very physical. This stuff is not magic. It's just basic chemistry being applied from physics, being applied on a larger scale. So try to think about what's actually happening. This stuff is actually doing stuff to other stuff in a pretty simple-ish way. And then you can see just structure on structure on structure. So histones become beads on a string, sort of wraps up, and you get all these proteins that are just sort of taking a lot of DNA, compacting it ultimately into sort of what looks like our metastructure of DNA, forming telomeres, forming a chromosome, which is now inside of the nucleus. And what's going to happen as we continue to zoom out in the next lectures, this nucleus is going to be inside a neuron, so we're going to talk about a neuron, and this is going to be the same nucleus inside of it. this same nucleus that's going to make the proteins that are going to be the neurons, the neurotransmitter receptors, and it's going to be the same enzymes are going to be made in here that are going to make our neurotransmitters. So then you're going to see a neuron, we're going to zoom out, we're going to see a circuit, so this connecting this with multiple neurons. Then we're going to zoom out, we're going to see a brain, and ultimately we're going to zoom out, see the milieu that that's in, the person, we're going to see the environment that it's in, and then we're going to have a moving picture of where this happened over time, how this brain has changed over time, how this person has changed over time. So we're going to be able to take any second and sort of zoom in and zoom out as is necessary to sort of get some level of understanding. And so I'm going to try and do some of this today to show you how it's actually pretty cool, I think. Besides Peter, does anyone know who this is?
My t-shirt.
Who?
Darwin.
Darwin, it's Darwin, close. But again, so gradual is a relative word, and evolution doesn't just happen gradually. Evolution, and that's a whole aside, but Darwin was awesome, but not right on everything. In fact, some of what we're going to be talking about is Lamarckian evolution. So not all evolution is genetic in the way that Darwin said. There's Lamarckian evolution, and we're going to talk about that next week, and it's actually very, very important in human beings and in all animals. So here's the sort of nuts and bolts. It's just machinery. Just think about it like a machine. It's an assembly line that's got to go through these steps to make things happen. So here's DNA. See this here? What's it made of? A, C, T's, and G's, right? It's the same thing here, right? So I want you to see this picture and then apply it to this, right? Because this is really a double-stranded DNA. This is just A, C, T's, and G's. So all of this is just this that's just folded, etc. So we're superimposing pictures on pictures to sort of see how this is functional. You've got, again, an enhancer region and a promoter region. This is where the transcription factors come in. Transcription factors bind. It does some stuff to expose. So RNA polymerase is always around. But this binding site is not always around. And so anything that can affect the availability of this binding site to RNA polymerase is going to increase this direction of the pathway, which ultimately leads to protein. So stuff's going to happen here. The epigenetic stuff, it's all going to happen here. It's going to change how exposed on a regular basis, how easy it is for transcription factors to get here over the lifetime of the molecule, which is super cool, but we'll talk about that next week. Do I sound really nerdy saying super cool about epigenetic? Okay, I'm all nerds. Good. So this stuff, transcription factor comes in, it does some stuff. It'll either be methylation, typically of C plus G islands, or it'll be sort of histone acetylation. And so again, well, there's more on that next week. So the RNA polymerase will bind here. You'll get transcription, and then you'll get here again. This is still ACTs and Gs, right? ACTs and Gs in a line. It's just connecting all this stuff. It's lots of cool stuff can happen. It doesn't have to be direct one-to-one. It can take A and B. It can take A and C. It can take B and C. So there's lots of different things that can happen. And you can think about this like an F-then sort of signal. F this binds here, then this. And the same signal can have different, the same if can have different thens in different molecules. And we'll talk about that, why that is. Like all of our genes have the same DNA. You want to know why our cells are different? There's one word. It's epigenetics. So it is, the reason your muscle cell is different from a neuron, is different from an eye cell, the DNA is all the same. The only difference is through exposure to certain things that we're sort of learning about now, we have epigenetically modified our DNA so that the patterns of expressions of proteins that it has makes it look like a neuron, or makes it look like an eye cell. And that can happen based on our experiences to any neuron. And that's sort of a cool phenomenon. So anyways, we get here, this is ACTs and Gs. This poly A tail happens here. This is actually sort of important, and they never really talk much about that. This can determine stability of the mRNA. So the more stable mRNA is, the more it can get, the more it can get translated into amino acids at the ribosome. So what we're seeing is lots of different ways to either increase or decrease the amount of this protein and the function of this protein, right? So the more exposed this is, the more transcription factor is going to work. The more exposed it is, the more the baseline rate. The more the poly A tail, the longer it's going to stick around, the more it's going to get put into this. So this step is a pretty cool step, and it's an important step. So this is ACTs, actually this is ACTs and U's, or U's. Yeah, because this is mRNA at this point. And all that this does, it goes through this reading frame and it says XXX, so ACT, or ACU, stick in this amino acid. TTC, stick in this amino acid. So there's a code, and it's the same in all humans, that each 3 in a line stick in one amino acid. And again, this is very much a very physical way that this happens. So this gets read, it gets translated into a string of amino acids. The amino acids then get processed through a lot of different things that actually the neurotransmitters do. So when you hear about like protein kinase C or inositol triphosphate, these things that we don't like to think about, it is doing the steps in here, and that are giving it its tertiary form and its structure. And the way that this stuff happens is oftentimes this stuff needs to get phosphated again to be active, right? So when you think of these second messenger cascades, something needs to be phosphorylated, and then it can do its thing. Because otherwise, it looks like this. You phosphorylate it, it does this, and then it's got the structure that it needs to sort of lock and key, if you want to think about it that way. And then, there's proteasomes that break that down. So turning up or turning down a proteasome can change the amount of that protein. And these proteins are obviously very, very important. And this is sort of, I'm supposed to talk about one other thing here. The idea is thinking about predictive powers of things. So, if Carrie were to walk up and just smack me in the face, right? I would predictably sort of turn to the side, go down, probably cry in the corner, right? We can sort of predict what might happen because we have an understanding of metaphenomenon, right? If I push something, it falls down, that sort of thing. Well, until you observed it and looked at it and been critical about what's going on, you can't learn what might happen when you do things. So this is, again, very nerdy, but I just pulled up the chemical structure of all of our psych drugs. And I encourage you to do this. In fact, I should probably just make a slide and send it to you. And then I'll leave some blank. And you will be able to tell me whether this drug is active in the brain or not. You'll start seeing patterns. And again, I'm not good at this, but you will see patterns. You'll say, hey, this looks different than the rest of these drugs. And the benzene rings, it makes it sort of lipid soluble. You'll see why certain, Zyprexa looks a lot like clozapine. And in fact, it looks the most like clozapine. And you can see that they're very similar in their mechanisms. And you can almost start to sort of see patterns and almost predict what things might do. And the reason that I bring that up is that SSRIs look very different. In fact, they are very different. And that's why, if all SSRIs did was be SSRIs and they all sort of did the same thing, it would not make any sense to switch from one SSRI to another SSRI. But switching from one SSRI to another SSRI, or one SSRI to an SNRI or an acid drug, or whatever, same results. Because they're not just SSRIs, they're actual molecules. SSRI is a label that we apply, because we like to think that antidepressants is a label that we apply, which is insanity to me. But the idea is that once you sort of start seeing these drugs for what they are, the chemicals that are interacting in the system, it lets you sort of make sense of it a little bit, to me at least. So this was also in the slide. So we're going to do our first sort of connections. We're going to connect genes to neurotransmitters. So I'm not going to talk a lot about neurotransmitters. Y'all are going to talk a lot about neurotransmitters. I'm just going to talk about the basics of what a neurotransmitter does at some point. So here's our friend serotonin, all right, 5-hydroxytryptamine. Up top, we got tryptophan. Tryptophan is an essential amino acid, right? So to make tryptophan in our body, we need to, all right, that's behavior. That's sort of already on the meta level. This is the rate limiting step. I don't know. So 5-hydroxy, this is the rate limiting step, tryptophan hydroxylase, right? Still, eating a lot of tryptophan, you can push the direction this way just because of chemistry. But this is mainly 90-something% what's going to determine how much serotonin you make. What is tryptophan hydroxylase? It's an enzyme. It's a protein. What do you think makes it? What makes all the proteins that are found? So it's made from DNA. It's made on chromosome 11 or 12. There's a tryptophan hydroxylase gene, right? So to make tryptophan hydroxylase, we're going through this exact same thing, which is in this metastructure of things, okay, on chromosome 11. So we can start to think about this. The thing comes in from the signal, from a neurotransmitter, comes in, that's going to ultimately signal this neuron to make this whole process go on. And we can see how tryptophan hydroxylase levels can go up or go down at any of these important steps. If it's been epigenetically coded to make more or less, it goes up or down. If it gets more poly-A, it goes up or down. If it, and then this gets into function. Not all tryptophan hydroxylases are created equal. And this gets me to the point of SNPs, which is super important. So who knows what a SNP is? Sigma-nucleotide polymorphism. Who knows nothing about SNPs? Perfect. Are you a med student?
First year.
First year med
One
student?
month, yeah.
Awesome. She is going to explain to all of you what a SNP does, okay? So based on only knowing, and no pressure, you can ask a friend. You can ask Dr. Hobbs. So